Hi, I'm Liz Fassbender. I'm the application scientist for CZID, and today I'm going to be talking about the tool and how you can use it to analyze metagenomic data sets. So this pipeline will take the output from your sequencer. So the FASTQ files, you could upload it onto CZID, and we will subtract the host reads, assemble the reads, and align to a reference database. And then you'll get an output of all of the taxa that are present in your sample in the form of a sample report. Not only do we have this metagenomic module, but we also do antimicrobial resistant detection. We have a module for generating SARS-CoV-2 consensus genomes, a generalized viral consensus genome pipeline that you could kick off right from your metagenomic data set, and a SCA-based phyllo tree. So you could take your analysis downstream of just metagenomic findings. So there's many use cases that you could do with CZID. There's mystery illness, so what is making someone sick? What is the etiological agent of this disease? Detecting antimicrobial resistance within the sample, novel pathogen detection. Our pipeline is very sensitive and can detect divergent viruses. Determining what microbes are present within the sample, doing microbiome studies, and identifying potential outbreaks and how the microbes in your samples are related to each other. So I'll go over how CZID works. So once you upload your FASTQ files, we find matches in NCBI. So we compare to the nucleotide and protein databases in NCBI and support the detection of not only bacteria or viruses, but fungi and eukaryotes as well. And then you get a per sample taxon count and tools for analyzing and visualizing your data, which I'll show you some examples of. So I'm just going to go over the pipeline as an overview of what happens, but I would like to say that we do have a more in-depth pipeline visualization in the tool where you could see every step of the pipeline that is run. So once you upload your raw reads, the first step is to remove any human or host reads and low quality reads. So the first step is to truncate to 150 million reads if you have over that per sample. And we do this to keep the pipeline running quickly. Then we use STAR to filter out host reads. We use Trim-O-Matic to trim Illumina adapters and PriceSeek to remove low quality reads. Then duplicate reads are collapsed using an in-house tool called CZID dedupe. Remove low complexity reads. And then we use Bowtie2 to filter out the host. And if there's still greater than 2 million reads present at that time, we'll subsample to 2 million, again, to keep the pipeline running quickly during the assembly and alignment steps. And then we use GSNAP to filter out human reads again. I'd just like to point out that human reads are removed in multiple steps during the pipeline, regardless of what host you choose upon upload. And we make sure that all human reads are scrubbed from CZID, so there won't be any human genetic material on the application. Once the reads are cleaned up, they are mapped against NCBI. So again, they're mapped to the nucleotide database using Minimap2 and the protein database using Diamond. A primary accession is found for each read. So here in this diagram, the color represents a different taxa. A BLAST database is generated on the fly based on those initial accession findings. Then the reads are assembled into contigs using the de novo assembler spades, and the reads are aligned back to those contigs using Bowtie2. Then we blast each contig against the database of putative accessions generated in the previous step. So those contigs are blasted against that BLAST database that was created on the fly. And then each read is assigned a final accession. So if it assembled back to the contig, it's given that accession, the same accession as the contig. And if the read did not assemble to the contig, it's given the initial read accession. Then we use NCBI's accession to taxon database to assign a taxon per content and compute statistics such as reads per million per microbe. So the runtime for each sample is typically around 1 to 3 hours, depending on the data side. The samples are run concurrently, so it isn't 1 to 3 hours at a time. They're all run together. And then once you log into CZID, each project will be organized into folders. And on the left side of the page, you will have different filters to use for finding samples and projects of interest. One of the first steps that you can do in CZID is see how your reads fared through the host filtering and QC steps of the pipeline. We offer numerous quality control metrics, but this is an example of my favorite one, which shows how the reads were lost. So for each step of that host filtering and quality control steps, you could see how many reads were lost and how many final reads you have. And you could view this as absolute values or as a percentage if you want to compare across samples. Once you're ready for analysis, you can go into your sample report page and you can apply filters to hone into what's important to you. So the pipeline is definitely more sensitive than it is specific, and this allows for multiple use cases such as identifying divergent viruses. But what you could do to remove any spurious hits or even contamination is apply these threshold filters. So here I have 2 filters applied. One is saying that I only want to see 10 or more reads per million, see taxa with 10 or more reads per million aligning to the nucleotide database, and at least 1 or more read per million aligning to the protein database. The 2 numbers for each column represents which database the taxa had homology to. So the top number is the nucleotide database and the bottom is the protein database. And you can toggle which is bolded depending on what you're interested in. If there is a taxa that you're interested in looking at further, you could click into the sample report and see how the reads align to the reference accession. So this is showing exactly how many reads and where they align to the reference accession, as well as the content that aligned. We also have the ability to add a background model. So if you run blank samples with your library prep, you can upload those as well as your samples, create a background model, and then apply it so that you can remove potential contaminants from your sample report. And then we have downstream visualizations. So this is an example of a heat map created. So I could view multiple samples at one time. I can also add metadata to the samples so I can identify patterns across my project. And then everything is available to take off of CZID. So we have bulk download of sample reports and FASTQ files. The raw files are only available to those who've uploaded the data. So you can download the non-host human scrubbed FASTQ files and upload those to the sequence read archive. And then here's an example of our interactive pipeline visualization. If you click into any of these steps, a modal will slide out that gives you access to intermediate files, tells you what the step is and what it's used for, and the parameters that were used. I want to talk a little bit about security and compliance. So as I've stated, human reads are scrubbed upon upload. The data is encrypted at rest and end-to-end in transit. There are regular security and privacy assessments, including penetration testing and security audits. And clinical specimens are safe to upload when they are de-identified. So when you upload your metadata, make sure that everything is de-identified. So we do not allow any PII to be uploaded onto CZID. We do have a security white paper, which could be accessed on our site at czid.org if you want to read more about our security and compliance. And own your data and decide how it's shared. Your data is always yours. The raw sequencing data is never shared with any CZID user. It is only available for the person who uploaded the FASTQ files to begin with. So we do have a help center to help learn about interpretation, analysis, and just understanding the metrics that CZID surfaces. So there is a tiny URL link to our help center, but there's also links within the app and under the resources tab on czid.org. And then there's also access to wet lab protocols via our partners at the BioHub. The Rapid Response team has put together a number of protocols and guides to help get you started in the wet lab. So you can access CZID through this Request Access tab, and you should get an account within 48 hours. Thank you for watching this presentation, and feel free to contact us if you have any questions.